Yeah, we continue with the stochastic processes playlist and specifically Poisson processes. And I come to the last video on Poisson processes. Of course, it's not that does not mean that we won't have to still talk about Poisson processes in other aspects of the playlist. This is just like a subgroup of videos talking about Poisson processes. I know when we still get to things like Q theory, we'll talk about Poisson distribution for arrival times and things like that. So, but for core Poisson processes, this is the last video the sixth of the range of videos. So you have applications of Poisson processes in this case. Let's see. Of course, we've been mentioning the applications a whole lot, but we want to look at them a bit more intently. So applications of Poisson processes. This lesson explains the applications of Poisson processes in telecommunication, traffic modeling, reliability engineering, and it includes worked examples and Python simulations. So let's go straight and talk about Poisson process definition just as a refresher. So, um, okay, let me just f focus on this first. So a Poisson process models random events occurring over time, and the assumptions include independent increment, stationary increment because of constant rate of lambda, and then we have rare events in small intervals. So they are made up of rare events in small intervals. So the key results for Poisson processes, we know that number of events in time, maybe it's arrival or number of calls or whatever you are considering. So it follows Poisson distribution with parameter lambda t, and then probability of k events is given as probability n of t equals k, which is equal to lambda t raised by k raised by minus lambda t over k factorial. And then for the entire arrival rate, that follows exponential distribution. And then we have t following exponential distribution with a parameter lambda. So first, then we go ahead to talk about application of Poisson processes in telecommunication. So Poisson processes are used to model incoming phone calls, packet arrivals, messages in networks, and events occur randomly with constant rate lambda. Okay, so a very good example of that will be seen here. A call center receives five calls per minute. So probability of exactly 3 calls in 1 minute would now be lambda is 5, that's 5 calls per minute. That's the rate of calls per minute. And then time is 1, right? So probability that n of 1 is 3 is now, lambda t, that's 5 raised to power 3, which is k, e raised to power minus 5 all over 3 factorial. And of course, we can write a Python code to implement that. That gives 0.1403. So for you to actually understand that, that's exactly what we've done. So I now I just do the actual 5 raised to power 3 exponent minus 5 and divide by 3 factorial like this here. So, and then we talk about probability of number of calls in 30 seconds. Probability of no call, sorry, probability of no calls in 30 seconds. In that case, now that means that k is equal to 0. So in that case, now if we have, so for k equals 0, of course, we have lambda t is 5 times 0.5 equals 2.5. So since k is 0, so it means that lambda t raised power k, that's lambda t raised power 0 will be 1. So we just have e raised power minus 2.5 all over 0 factorial, which is also 1. So we have e raised power minus 2.5. And of course, that if you do that, you get 0.0820. So that's the probability. So there's an 8% chance that no call comes in 30 seconds. Now, by the way, 30 seconds is actually half of a minute. That's 0.5 minutes. And that's why we have that right here, 30 seconds. So because we're talking about minutes, right? So now, then we go for inter-arrival time. So you can talk about the time between calls, which follows exponential distribution with lambda equals 5. So probability next call takes more than 10 seconds will be t greater than t, which is e raised by minus lambda t. So, and for this t now, so if we evaluate all this, we get the t to be 10 over 60 because 10 seconds, right, so you have to convert it to minute. That's 10 over 60, which is 1 over 6. So probability t is greater than 10 over 60 is equal to e raised to minus 5 times 10 over 60. And if we evaluate all that, we get 0.4. So there's a 43% chance that the next call takes more than 10 seconds. So that is the application of Poisson processes in telecommunication. How about the application of Poisson processes in traffic modeling? So modeling the traffic flow. So for instance, you can use this for cars passing a checkpoint and pedestrian flow. So vehicle arrivals at intersections, right? So imagine you have, for example, two now. Cars pass at 12 cars per minute and probability of 10 cars in 1 minute. So if you need probability of 10 cars in 1 minute, right? So it means that probability that n is equal to 10. That's uh, arrival rate is 12 and time here is 1 minute. So we are talking about the minute. So 12 times 1 raised to power number of cars, that which is 10, e raised to minus over 10 factorial. Then we can, of course, write a code for that. So if you do see this, it means there's a 10.5% chance that there'll be 10 cars in 1 minute. What about probability of at least one car in 5 seconds? At least one car in 5 seconds. So that means the lambda of t is equal to 12 times 5 over 60, which is equal to 1. So that's probability that n is greater than or equal to 1, which is 1 minus probability of 0, right? So, and that is equal to 1 minus e raised per minus 1, because probability of 0 will be, lambda t raised per 0, which is 1 already, then e raised per minus 1, like that. So, and that's computed will give us 0.63. So there's a 63.2% chance that there'll be at least one car in 5 seconds. So what about waiting for the for next car? So so we are talking about timing now. So and time follows exponential distribution with 12, right? That is lambda. So expected value now will be 1 over lambda, which is 1 over 12. And when computed, you have 0.08333. That's like an 8.3% chance that okay, the 0.08 minutes for to wait for the next car, something like that. Then we go on to application of Poisson processes in reliability engineering. It is used to model machine failures, of course, maybe in a manufacturer, in a factory or something like that. So system breakdowns also can be modeled using that. Then component lifetimes. So failures occur randomly with rate lambda. So we already know the whole idea of Poisson processes for rare event that occurs, that occurs at intervals. So, for example, three, now imagine that you have a machine that fails, you want to, a machine fails 2 times per week. That's the rate of failure now. So that's the lambda 2 times per week. So probability of 4 weeks, 4 failures in a week now. That's probability n is equal to 4. So so here now you have 2 times in a week, 1 week. So the time unit here is week. So that's 2 failures in 1 week. That's lambda is 2, time is 1. So you have 2 times 1 raised per 4 failures, e raised per minus 2 over 4 factorial. And then, of course, you do that, and you have a 9% probability that there'll be 4 failures in a week. That's a bit low. Then you have probability of no failures in 3 days. So probability there will be no failures in 3 days. A week is 7 days, right? So 3 days, that's 3 out of 7. So lambda is 2. That's the not machine fails 2 times per week. So lambda is 2 now. Then in 3 days you have 3/7. So no failure. So probability n equals 0. That'll be e raised per minus lambda t. And if you simulate that, you get 42.4%. That's 0.4243. That's a 42.4% probability of no failures in 3 days. Then what about you want to know the time it takes before a failure occurs in the system? So time until failure. So time follows exponential with lambda is 2, right? Because there are 2 failures in a week. So probability t is greater than 2, it will just be e raised per minus 2 lambda. E raised per minus 2, right? Because in a week you have that's 1, so minus 2. So reliability function, now you have R of t equals e raised by minus lambda t. That's the formula we have used here. So lambda is 2, t is 1. All right. So in that case, now if you do this, so time until failure will be like 0.13 weeks. All right. That's like 13/100 weeks, or you can just try to convert that. So we do simulation of a Poisson process. So we simulate arrivals using exponential inter-arrival times. So you have lambda is 5, time is 10, t is 0, and then you go on with the simulation and get, of course, the kind of picture we keep getting when we simulate that. So you have the Poisson process simulation, and it just keeps going like that. And as you keep running it, it keeps changing for sure. So 50 now, something about 50, 60 now, back to 50, and so on. Yeah. So it just keeps going like that. So in summary, we say that in summary, right? We have application. So application of Poisson process in telecommunication. It is the model events are calls, number of calls that comes in packets in a, you know, like like you're talking about flow of data or something like that. So example would be calls per minute. For application in traffic, you use it to model events like vehicles passing at a point. So that's cars at a checkpoint or at a roundabout or whatever you want to focus on. Then in reliability engineering, you want to model failures and machine. So that's in terms of say machine breakdowns. So the key idea is that the number of events follows Poisson distribution with lambda t, and interarrival times are exponential, and they're widely used in engineering and data science. So, for practice problems now, okay, so we have all these questions segmented like that. So we have a call center receive 4 calls per minute. Find the probability of exactly 2 calls in 1 minute. Uh, so maybe I try to do one question in each group. So a system gets 2 alerts per minute. What is the probability of more than 3 alerts in 1 minute? So let me take that 7. So a system gets 2 alerts per minute, 3 alerts in 1 minute. So that's question 7, right? So 2 alerts per minute. That's lambda right there. Then the next thing now, a system gets 2 alerts per minute. What's the probability of more than 3 alerts in 1 minute? Probability more than 3 alerts in 1 minute. So that's probability number is greater than or equal to is more than 3. That's probability n is greater than 3. Probability n of 1 is greater than 3. That's what we are looking for. Probability more than 3 alerts in 1 minute. More than 3 alerts in 1 minute. So don't forget, when you have more than something, that'll be 1 minus e raised per minus lambda t. So that works. So n is greater than or equal to this 1 minus e raised per minus lambda t. 1 minus, right? So here we have probability n is greater than 3. That is 1 minus e raised per minus lambda t, right? N is greater than k. That's what the formula looks like. N is greater than or equal to 1. T, okay, we already have all these formulas, in fact. N greater than or equal to 1. That's 1 minus this. Then 1 minus 3 is minus lambda t. Probability of more than 3 alerts in 1 minute. So this is for n greater than 1, actually. N greater than 1. So n greater than 3 also works here, right? So, um, okay, so I mean, we already know that once n is greater than or equal to 2, it becomes very small, right? So here we can just go for the fact that this is 1 minus e raised per minus lambda is 2, and the time is 1, that's in 1 minute, right? So that's equal to 1 minus e raised per minus 2. And that'll be approximately, uh, Desmos does the job for us now. So that's 1 minus e raised per minus 2. That is 0.8647. 0.8647. 0.8647. Okay, so I use the fact that so n greater than 3 automatically translates to the fact that n is greater than 1. And we know generally for Poisson, once n is greater than 2, the value becomes very small, like that. Okay, so yeah, I have a bit of concern about this, so let me know what you think about that. Then for traffic modeling, cars pass at 11 per minute. What is the probability of more than two cars in 10 seconds? More than two cars in 10 seconds. Okay. Vehicles arrive at 18 per minute. What's the probability of at least one vehicle in 2 seconds? A road sees 20 cars per minute. What's the probability of no cars? Yeah, I like this. A Yeah, and it's also tricky. So a road says 20 cars per minute, right? That's question 9 now. So a road sees 20 cars per minute, 20 cars per minute. Okay, so that's lambda right there. Then what is probability of no cars in 3 seconds? Probability no cars in 3 seconds. That's probability n is equal to 0. Probability n3. No, we can't even say this. So we need probability no cars in 3 seconds. So we started the standard already with minutes. So this is now talking about seconds. So we have to harmonize the two. Probability no car in 3 seconds now would be this. So we know 60 seconds make 1 minute, right? So 3 seconds is the same thing as 3 over 60 minutes. That's 1 over 20 minutes. So that conversion is very important. So um so that means that lambda is 20 now in minutes. Then what else? We need time now. That's 1 over 20. Everything is now in order. Then we also have what else now? We need k to be 0. So that means probability n of t is equal to k. That is lambda t raised to power k into then e raised to power minus lambda t all over k factorial. So that's probability that n at 1 over 20 is equal to 0 equals lambda t. That's 20 times 1 over 20 raised to power 0 e raised to power minus 20 times 1 over 20 all over 0 factorial. So that means 20 times uh 1 over 20 is 1. So that's 1 raised by 0, e raised by minus 1, all over 0 factorial, right? 1 raised by 0 is 1, times e raised by minus 1, all over 1. So probability that n of 1 over 20 is equal to 0 is equal to e raised by minus 1. And then decimals finishes the job for us. E raised by minus 1. E raised to power minus 1. So that's E raised to minus 1, like this. 0.3679. 0.3679. So that is approximately 0.3679. So there's a probability of roughly 36.8% that there'll be no car in 3 seconds. So let me see if I can take another one. So now that's on the traffic modeling. Then for reliability engineering, a machine fails 1 time per week. What's the probability of exactly 2 failures in 2 weeks? Um, okay, it fails 1 time per week. They were talking about 2 failures in 2 weeks. So I think I'll just go for that. Or should I go for maybe I should go for 20. They are all tempting. Okay, a system has failure rate 6 per year. What's the probability of exactly three failures in half a year? I like the idea of half a year so that because of the whole division thing. So a system has failure rate 6 per year. So we are looking at three failures in half a year. Lambda, so now lambda is 6 failures per year. So 6 failures per year for lambda. Then we're looking for probability of exactly three failures in half a year. Probability exactly three failures in half a year. In half a year. So okay, this is lambda. So half a year is 1/2, which is 0.5. So that means we're looking for probability that n at 0.5 is equal to 3. So this is what we are looking for. So, and we know that probability n of t is equal to k is equal to lambda t raised by k e raised by minus lambda t all over k factorial. So now t is 0.5, k is 3, lambda is 6. That's 6 failures a year, right? So with this in place, then we have that probability n of 0.5 equals 3 is equal to lambda t. That's lambda is 6, t is 0.5, raised power 3, right? Then e raised power minus 6 times 0.5 all over 3 factorial. So that is 6 times 0.5, that's 3. 3 raised power 3, then e raised power minus 3 all over 3 factorial. So that's approximately 3 raised power 3 raised power minus 3 over 3 factorial. 3 raised power 3, 3 raised to power 3, e raised to power minus 3 divided by 3 factorial. That's 0.2240. 0.2240 approximately. So 0.2240. So that translates to a 22.4% chance of failure, like that. Yeah, so with this, we come to the end of this interesting video about applications of Poisson processes. So you have a bonus challenge. The Poisson process has rate lambda equals 5. Find probability n of 2 is 6, n of 2 is greater than or equal to 1, t is greater than or equal to, t is greater than 0.5. So don't forget you have the formulas to use up here already. Let me know how helpful this is for you. So don't forget to try the 7 questions on telecommunication, another 7 on traffic modeling, another 6 on reliability engineering, and the bonus challenge also. So let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to the channel already, I thank you very much for doing that. If you haven't, what exactly are you waiting for? Go ahead, subscribe right now and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos exclusively or getting to see some videos first. You can request for PDF copies of my notes. We can hang out together online or physically if you're in the same geographical location at any point in time to discuss whatever interests you on my channel, be it mathematics, data analysis, data science, machine learning, and all of that. Scholarships, whatever interests you here. Um, Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.